All right, try it again. Perfect. Oh, we had it there for a second.
So close. Sorry.
So close. Okay.
Okay.
Yeah, perfect. That looks good from our end.
Okay, great.
All right.
Um,
I'm gonna just give everyone in the room here another second to filter in, and then we'll take it away.
awesome.
Cool. Thank you. Is anyone else out there? I think we're good. Should we get going? Yeah. All right. Thanks everyone for coming back. Hope y'all had a good lunch. Our next talk's gonna be Daniel Otto. The website is being updated if there are any small changes in the schedule, so keep an eye on that. Folks who are presenting tomorrow, there's a Google Drive link on the website. You could drop off your talk so we could get it on the computer that I'm using to run all of this. And folks who presented today, if you wouldn't mind uploading your talk, that could be really helpful as a reference when we look back, especially on Friday, doing the white paper. Any other announcements, things to consider? All right. Well, in that case, Daniel, the floor is yours. Take it away.
Great. Thanks a ton. Yeah, hello everyone. Sorry I couldn't be there in person, but thanks to everyone who organized this and put this together. It's a really cool workshop. Yeah, happy to be talking about some of the research I did or am currently working on, but field season that I did this last year. Yeah, so this is a project I'm working on with Mira Birdall and Jess Badgley at University of Washington. And kind of goal is to just show what we've accomplished so far and some preliminary results. Yeah, so this project, kind of the history of this is that this started as actually as like a student project working as faculty. Jess and Mira and I were all faculty at one point or another. And then we've kind of expanded it from there and then had a very successful field season this last year. So yeah, we have a great data set now and really excited to hear people's thoughts about it and ideas of what to do with it. Um, yeah, also just huge acknowledgement to a bunch of people who I'm sure are in the room there who had a huge hand in making this happen and were up at Research Camp last year. So huge thank you to all of them. All right, as a brief refresher, so temperature lapse rates, change in temperature with elevation. As you go up, it generally gets colder. And models of glacier evolution commonly estimate melt using near surface temperature, which is typically taken from weather model or climate model, just some kind of weather reanalysis. And because model grid scales are coarse and our models need temperature at each point on the glacier surface, climate model data is often downscaled using a lapse rate. So because weather observations in glacier areas are sparse, studies typically do one of two things. They either estimate the lapse rate using an off-ice weather station, or they use some kind of standard lapse rate, usually -6.5 degrees per vertical kilometer. And so this approach kind of implicitly assumes that off-ice temperature changes are proportional to on-ice temperature changes, which isn't necessarily true. And although the assumption is often necessary just for data constraints, I argue that we don't necessarily have a good understanding of when this assumption is valid or what the impact is of relaxing it in our models. However, we do have a good understanding of how lapse rates change regionally across different climate regimes. So physically, the lapse rate depends on temperature and the amount of water vapor in the air. And in cool maritime climates, such as Juneau, small lapse rates 10 or closer to -4 degrees per vertical kilometer are typical. And then you have, as the air is lifted up and over the mountain, water condenses, precipitates, and you have drier air coming down the other side. The descending air has a lower heat capacity because it's drier, resulting in larger lapse rates, heats up more quickly, larger lapse rates in continental regions closer to 10 degrees per vertical kilometer. And knowing the lapse rate is really important for accurately modeling glaciers because the amount of melt area is very sensitive to the lapse rate. So we have here is two different scenarios, one with continental lapse rate, one with a maritime one. And if we assume a uniform increase in temperature with elevation, we see that the 0-degree isotherm rises, and that our smaller lapse rates amplify changes in the melt area for a given warming. And this is especially true for glaciers that have a really shallow slope. So this is particularly important for modeling global glacier evolution because this is such a sensitive parameter. It's necessary to better understand the lapse rates in glacier environments, particularly like at the glacier surface, in order to kind of accurately model future change in melt and the glacier response. So this brings us to the Juneau ice field. The ice field spans one of these maritime continental climate transitions, condensed to about 60 kilometers over the coast mountains. And what's unique is that it's linked by a continuous ice surface. So there's not that many places that you can kind of follow the same strip of ice from the maritime side to the continental side, which makes it a really unique natural laboratory actually for studying lapse rates on glaciers. And lapse rates are relevant to the ice field in particular, because the ice field's low slope angle makes estimates of future change really dependent on knowing the true lapse rate and also understanding what the link is between lapse rate and melt. So we designed a study to answer these questions. Yeah, so what we did is we kind of scattered all of these small weather stations over the course of the ice field. The animation here is kind of showing all the different locations and the temperature time series associated with all of them. So we had 26 of these kind of low cost, inexpensive standard temperature sites, and then we had 5 intensive sites that show or that record a lot more of the meteorological variables. And this is kind of in addition to all of the existing JERP data, the camp weather station records, the Nunatak camp weather station records, as well as all of the snow pit data that's collected. So where possible, we located our sites along with the snow or at the snow pit locations. So these are all put out kind of in mid-June and collected about the end of July, early August. So I just want to talk briefly about what these sites actually look like. So our standard sites, we had temperatures at 2-meter height and 1-meter height. And we used small, kind of inexpensive hobo pendants, about $80 each. And the materials for the site itself only maybe cost, like $10 or so. So it makes the whole thing relatively inexpensive compared to a whole weather station. They're also 99% organic, shooting for 100% organic in the future. We tried to make these all of natural materials. So the pole's bamboo and it's pretty much just wood and like a couple zip ties is the 1%. But yeah, this design I think really made it possible to kind of keep all these sites on the glacier surface and to have a geographically dense network of sites kind of across the ice field. And then our intensive sites, we had 5 of these, which were spanning the ice divide. And these are kind of our link between lapse rates and melt rates. So these have a bunch of meteorological variables. They also have an ablation stake with a time-lapse camera pointing at it so that we can see the time series of melt in association with the lapse rate. So to jump into some preliminary results, so we're going to focus here on just the kind of long transect that goes across the ice divide. We're just starting to analyze this data, but yeah, kind of focusing on the maritime continental question. The intensive sites here are marked with the stars. So there's 1 at the divide and then 2 on either side of the mountains. The prevailing wind direction is typically from the maritime side to the continental side. So I'm also kind of calling the maritime sites windward sites and the continental sites lee sites. So you'll just see that in some of the later figures. And then the intensive sites are at the same elevation on each side. So the upper windward site is directly comparable to the upward lee site. And so here's just showing an example of what this data looks like. So on the top here is temperature. The bottom is the calculated lapse rate. Um, so for the temperature plot, the highest elevation site is in green and the lowest elevation site is in blue. And I just want to draw your attention to the shaded periods as well, kind of the end of June and then kind of the end of July, because these have turned out to be particularly interesting. So in the first, we see that the lowest site is consistently the warmest site, and that the upper site is consistently the coolest, which I'm realizing the legend might be actually a little bit backwards here. Anyway, the first period, the lowest elevation site is the warmest, upper elevation site is the coolest. This first period is the period where we have stable lapse rates. It gets colder as you go up. The second period, we have the reverse pattern, which you can see in the bottom plot here is correct, that the lapse rate is inverted. So we have positive lapse rate. It gets warmer as you go up during the second period. And so, yeah, so we see the same thing between the maritime side and the continental side. And then if we do the calculate the lapse rate for both sides, we can compare, we can start comparing the lapse rate or what's going on in the lapse rate between these two periods. So on the left in blue is the maritime lapse rate. On the right is the continental lapse rate. And then the shaded area below zero marks this like normal stable period. And the area above zero is the positive or inverted lapse rates. So as you can see, we see the same kind of stable and inverted period between both sides of the ice field. And then the bottom plot there is kind of showing which times the lapse rate is negative, is the colored part, and then the gray part is the same, which times the lapse rate is inverted. And then if we look at the statistics over the entire period, we see the box plots that show here, the median and the distribution of the lapse rates over time. So the first plot shows the entire period, and I've also split it up here, the other two plots based on whether the lapse rate is negative or positive. So if we look at the whole period, we get lapse rates of -2.2 for the maritime side and -2.8 for the continental side. And so these values are both kind of quite small from what we expect from that kind of standard 6.5 degrees per vertical kilometer. But once we split off the inverted period, we get much more reasonable numbers, -4.5 and -5, both within our theoretical kind of expected range of lapse rates in the atmosphere. And note that the differences between the maritime and continental lapse rates are pretty consistent between all three of these groups. It's about 0.5 degrees magnitude larger on the continental side for all of them. So we are able to detect this difference in climate regime between the two sides of the ice field. And that this difference is like relatively small between maritime and continental is particularly interesting. And there's lots of reasons that this could be the case that I'm planning to investigate. But it's particularly interesting that the change in lapse rate between climate regimes is so much smaller than the change when there's an inversion. So it's 0.5 degrees between maritime and continental versus an 8 to 10 degree difference between the stable and inverted periods. So this is actually a great opportunity to kind of test the second half of the research question, which is how does the lapse rate actually translate to melt? So here I've plotted the cumulative positive degree days based on the 2-meter temperature at each of the intensive sites. So the blue again is maritime, red is continental, purple is the site that's at the ice divide. And the same two stable and inverted periods are highlighted. So if temperature is proportional to melt, as something like a positive degree day model would assume, we'd expect that there's not too much difference based on this in melt between the maritime and the continental sides, and that the inverted period represents kind of a significant melt event. So this is reflected in the calculated degree days. You can see that all the sites are within approximately 50 degree days of each other, which corresponds to about 0.25 meters of melt. And there's not really any clear relationship between continentality and degree days. And then comparing the two shaded periods, the the slopes are overall steeper during the inversion, which corresponds to expected higher melt rates. And so the question is, do these represent reality? And fortunately, we have the data to find out. So as I mentioned earlier, we had time-lapse cameras at each of the intensive sites pointed at an ablation stake. So we can look at the real melt rate over time and kind of associate it with the lapse rate between these two periods. I'm skipping over this now, but I will show this slide again because it's really fun to watch. Okay, so here's the actual melt data. This is transcribed from the time lapses. Note that there are 5 intensive sites, but only 4 time lapses. Sadly, one of the sites had a problem, but I put the overall melt that was recorded at that site on the plot here as a comparison. Note that the units here are in depth, not in SWE. Yeah, and then on the right, the box plot shows the melt rate between those two, the stable and inverted periods, with the stable period being the darker box plots and the inverted period being the lighter ones. And so these are kind of small sample sizes. Don't have too many data points for each period, but I think we can be pretty confident in saying that the melt rates were at least the same, if not smaller, during the inverted period, particularly at the high elevation sites. And we can also see from the time series that over the course of the season, melt was much higher on the lee side than it was on the windward side. And so this is pretty much exactly the opposite of what we'd expect from the positive degree day model, which is great because it means that we're learning something. Yeah, and I'll caveat again that these are very preliminary, and I'm still investigating kind of why this is. I don't have solid answers, but I do have a hypothesis, which visually you can kind of see here. Yeah, if you've spent time in the ice field, you've likely experienced both of these days. Yeah, the hypothesis being, even though it is kind of bright and sunny and warm, it doesn't necessarily mean that warm air is reaching the surface. It could be kind of exactly the opposite, that especially if there's low wind, it might feel warm and sunny as we are standing at 1.5, 2 meters of height, but that right near the surface, the snow surface, there could be a cool kind of stable layer that is protecting the snow from warm air intruding from above. So bouncing off downdrafts that would otherwise be delivering energy to the snow surface and kind of preventing enhanced melt despite the otherwise warmer temperatures. And so while we can't really know this for sure at this point, one indicator would be if there was a large difference in temperature between 2 meters height and the air closer to the surface. And luckily, that's something that we can also check from the data that we collected. So on the left here, we have the temperature profiles from each of the intensive sites. We had temperature data at 2 meters, 1.5, 1, and 0.5 meters. And then on the right, we have the same kind of thing, the comparison between the stable period and the inverted period. And the y-axis of the box plot there showing the difference between the 2 meter temperature and the 0.5 meter temperature. And so what we can see here, at least in the preliminary sense, is that there is indeed a bigger difference in temperature between the upper air and the surface during these inverted periods. So this might be the mechanism or a mechanism for why we don't see the enhanced melt on these really warm, sunny days. And instead, if during the kind of stormier, cloudy days, there isn't much gradient in temperature between the upper and lower air, it might make it easier for melt energy to actually reach the surface and for turbulent mixing to cause additional melt. So yeah, that's kind of my working hypothesis right now, but plan to dig into it more. Would love to hear ideas if other people have thought about this or other suggestions. Yeah, just to summarize, kind of our inverted lapse rates didn't really correspond to enhanced melt despite looking very warm and sunny, and that the measured lapse rates, they do vary between the maritime and continental sides, but the difference is kind of surprisingly small, only about 0.5 degree Celsius per vertical kilometer. But that melt at the continental sites is substantially higher than melt at the maritime sites. So there's a bit of a disconnect there between those two results, which is worth looking into more. Yeah, and looking forward, hoping to go back this coming field season and collect more of these melt time series and associate them with more temperature data to kind of continue digging into this relationship. And yeah, excited to hear people's thoughts about the white paper and stuff. But yeah, just wanted to mention again that the drip camp weather station record, not something that I'm showing in this talk, but is an incredibly valuable resource for this kind of work. Yeah, and just want to give a shout out for all of the years of data that are there that are going to be incredibly useful for my work, and I know for many other people's work on the ice field. Yeah, and with that, I'm happy to take any questions.
Yeah, go ahead. Billy's got a question. Billy, go ahead on Zoom.
Thanks. I heard someone call on me, right?
Yes, yeah, go for it.
Um, that was really cool, Daniel. Thanks for all that. I guess I was wondering, with the bigger stations that have more meteorological data, can you do a full energy balance model with those? And do you think that you'd be able to better constrain the problem if you brought in other energy balance components?
Yeah, thanks for the prompt on that question. I would love to do a full energy balance assessment. I definitely don't have the instruments to do it right, or didn't put them out this last year. But I hopefully did everything I can to maybe estimate some of the components. Is kind of my eventual hope for this is to kind of constrain some of them, estimate some of them, and yeah, hopefully be able to say something about the actual energy balance as a function of the maritime continental transition. That's definitely a target. I would love to to learn more about doing this with kind of not all the right instrumentation, but that's definitely a goal and something I'd like to do in the future.
Yeah, hey, thanks for the talk. It's really interesting. Were there any differences between the solar radiation shielding on your different types of stations for the temperature sensors? They have a solar radiation shield or they don't, or it's aspirated or it's not.
Yeah, great question. We did all the sites with exactly the same shielding, or at least all of the standard sites have exactly the same shielding. The kind of intensive sites have they have kind of two different types of sensors, but we put one of the same exact sensors from the standard sites on the intensive sites. So we do have a like perfectly kind of comparable like set of data across all the different sites. Yeah, the way that we did it was we just wrapped the sensors in highly reflective material. Just based on some testing, we actually found that to be as effective or more effective than some of the standard radiation shields, just like kind of a mylar reflective fabric. And that's given us pretty good results. And fortunately, also one benefit of the lapse rate calculation is that if your biases are consistent between different sites, they do cancel out when you take the slope of the temperatures. So hopefully that's also working in our favor.
Yeah, great. Did they compare? You said they had a comparable one at the more advanced sites. How did the two different types of shielding compare at those sites? Just curious.
It's a pretty small difference. It does look like actually the slightly nicer sensors maybe have a little bit more solar heating bias than the like kind of cheap cling film or cheap wrapped sensors. I haven't looked into that too much, but yeah, that is something that I'm keeping an eye on and a little curious to learn more about why that would be the case.
Thanks.
Hey Daniel, nice talk. I have a quick question. You may have mentioned this, but I'm curious from some of your intensive sites if you are seeing a correlation with like wind, thinking about that like turbulent mixing on the days where you're seeing like more lowering.
Yeah. Wind has been something I've been thinking a lot about. And I don't have a clear story yet with wind. The data themselves don't show a super clear association, or there's not really a clear difference between the kind of stable and inverted period in the wind speed. So that's something that I would love to look into more. In particular, actually, I would love to look into reanalysis data and what the winds are doing in like the upper air over the ice field, and kind of how that is playing into it also. So yeah, I'm really excited about the wind story. I don't know what it is yet, but yeah,
Thank you.
yeah, thanks.
Go ahead, Billy.
Thanks. And maybe I can tee you up another question because you talked about measuring SWE versus measuring just a surface lowering. Like, would a systematic difference in snow density be able to produce these things if there's less dense snow on the continental side? Would you expect more melt for the same positive degree days because there's less mass, or is that off?
No, that's totally right. Yeah, that's something I was thinking about a lot, and I don't have uh, yeah, I don't have a perfect answer to it, and I'd like to do the actual like assessment of what that error would be, given kind of what we know about the ice field. But there were some fine folks out there taking firn cores, so there is some data there between the firn cores that were kind of taken in like mid-June, and then when the students came through and did their snow pits. So I'm looking forward to looking at that just to see what the difference in SWE would be, kind of between the earlier season conditions. Anecdotally, the ice field snow was as dense as ever. So I imagine that of the places that you could do this, this is probably the amount of compaction and density differences between the different areas is probably smaller. Hopefully, yeah, hopefully kind of a 10% error thing, hopefully less than that. So yeah, we'll hopefully be looking into that more, but I think there's data to actually constrain that as well.
Okay, was there a question from Kaya at the bottom?
Oh, less question, more comment. So decided to be less annoying and put it in the chat. I just think that maybe someone somewhere would be keen on using this to think about snow cup form. I was just like sitting here watching snow cups form and move and stuff. And yeah, there could be fun snow cup questions to be asked of this by people that are not me.
Yeah, there are it is really fun to watch the time lapses, and I'm sure, yeah, snow scientists would have a field day with it. There are a couple where you can kind of see the snow cups migrating, which is really wild. And you can also see there's a couple periods like in the middle of, I don't know, like early July, of course, that like, the divide gets like a foot of snow or something, and then immediately the sun cups show up again, which is really interesting. So yeah, a lot of just wild stuff in the time lapses.
I might chime in if nobody else has. I'll have a 30-second comment as well, maybe a minute. Like the plan for this coming year, Daniel and I discussed, is trying to focus on the Mathis Llewellyn, like transect, and then also install a transect that runs from kind of Divide going all the way down into Gilkey trench, with the idea that we're really keen on looking at land stability type questions in the trench, the lateral marks of the trench. So having an understanding of that, that's a pretty big elevation change across that. And then the third one, Dana, I don't think we talked about, but it'd be great for you to chat with Jess over here, who talked earlier with her interest looking at the local meteorological observations. You can imagine from Valley Wall, depending on where you're at in Icy Basin, you might have some thermal variations with a grid there that could be interesting to kind of capture, that might be input into your model that you're planning on working on.
Yeah, totally. A lot of exciting stuff planned for next year, and what I would love to collaborate with people who are also interested in doing similar stuff in the ice field. Or if you could use this data in your work, I'm also happy to talk. Yeah, there's so many different cool areas with their own microclimates. It's cool to sample the spatial variability. We only really touched on it last year, but yeah, there's a lot going on.
And I get, maybe this is also a question. I mean, we Dana, you and I talked about the comparison of your sensors relative to the RM Young sensors and the meteorological sensors. Do you have a sense of like range of uncertainty yet, or is that one of our big ultimate goals this summer, maybe?
Range of uncertainty in the lapse rates.
Between your sensor values that you're calculating and these other higher end MES stations that we're hopefully going to be comparing with.
Yeah, I mean the one thing that I'm really excited about with those is the wind sensor. That's it is always really challenging to get good wind speeds and directions and stuff, and having the kind of ultrasonic high tech wind sensor up there will be really nice. Um, the temperature data in particular, I think is actually really solid from this project. We put a lot of work into making sure that like that data is using kind of the best sensors that were available to us. So. Yeah, I'm honestly I don't know too well the capabilities of the Arm Young systems, but I'm really excited to have more equipment out on the ice field. Um, yeah, no, I think they'll compare pretty well. They'll be nice to have. Yeah, be nice to have those out there.
And Daniel, before we move on, Nestor had a quick question about how accessible the data are that you've collected.
Yeah. Currently, I'm still kind of in the process of doing some initial analysis on them and finishing up the processing of everything. Yeah, if you have an application or something that you'd be interested in either looking at them or incorporating them, I'm happy to talk. Yeah, not exactly sure what the timeline is for an official publication. But yeah, let me know if you have questions about that.
Awesome. Thanks, Daniel.
Great. Thanks, guys.